So this is a topic that comes up quite a lot in biology and actually in maths and a little bit in chemistry. But out of all the sciences, it seems to come up most in biology. But it's actually quite a mathematical idea. We'll start off just by recapping what does volume mean. If I drew a straightforward cube like this, not a particularly great picture, but or in fact any what are they called, cuboids. We just if so this could be, for example, three on the bottom. It could be 4 along there, and it could have a depth of 5. Then the volume is going to be equal to all 3 multiplied by each other. It doesn't matter which order you do them in. You could do 4 times 3 by 5, 5 times 3 by 4. It doesn't. They're all the same. It doesn't make any difference. So 3 times 4 times 5. That's going to be what the volume is. Now, if we say that that's all in centimeters, then really I should be really writing 3 centimeters times 4 centimeters times 5 centimeters. In fact, let me just pause that and I'll do that now. Okay, so when you multiply them all together, you end up with 60 centimeters cubed. So it's the amount of 3D space. Now you can, if another way you can think about it is that if I opened up the top, if this is waterproof and I opened up the top and I poured some water in here, then the amount of water I'd be able to fit in there would be 60 centimeters cubed. Incidentally, that is exactly the same as 60 milliliters. So a centimeter cubed is the same as a milliliter. Not important for this topic, but it is important. You'll come across this in science in other places. So a centimeter cubed is the same as a milliliter. Anyway, so we look at these little objects here, and we can see they're all made out of these little cubes. Let's just imagine that each cube is 1 centimeters cubed. So 2 of them would be 2 centimeters cubed, right? So we're going to just work out the volume of each of these shapes. Okay, so I'll just pause the video and you can do that. So the total volume of the one on the left, what you would do is I would suggest marking them and then writing subtotals. So I'd go 1, 2, 3, 4, 5, and chop that bit up and write 5 there, and then 1, 2, 3, 4, 5. It just means that you're less likely to make mistakes doing it this way. Okay, maybe what would happen to make it even better, I could even use a different symbol there, so I know that that's that 5 and that's that 5. Then I'll go this way. 2, 3, 4, 5, 6, 7. So that's 7 there. Then we've got 3 here. We can just write 3 there and 3 there. And we just add them all together. A good way to add, I can see straight away that's 23 because 7 plus 3 is 10, 5 plus 5 is 10. Then you got this other 3 over here. So that's 23. Now, you can do exactly the same with this, but there's also a little shortcut because if we have a look, let's use a highlighter for this bit here. This bit in the middle, exactly, yeah, that's right, you're right. So the bit in the middle, we could just say is 15, can't we? Again, I should really be using units, but I don't think it's really necessary for this bit. Yeah, exactly. So 15 plus 2 plus 2 plus 2 plus 2. So 15 plus 8 is going to be 23. So which one is the largest volume? The answer is they're the same. They have the same volume. Now, the next thing is, what about surface area? Can you calculate the surface area to volume ratio? Well, let's just calculate the surface area first. We'll look at what the surface area to volume ratio means in a moment. So what about the surface area? Okay, do you want to see if you can work out what that's going to be? So to understand surface area, let's go back to the cube for a moment. This cube, which is a lot easier to understand, it's got 6 faces. Hang on a second. So if we look at this cube just sitting on its own, then we've got this, let's use a highlighter here. We've got this face over here. That's going to be 5 multiplied by 4. So that's going to be 20 centimeters squared. Oops, squared. Remember the surface area is going to be in squared this time because it's centimeters times centimeter. Then we've got the one on the top. And that's going to be 3 multiplied by 5, so that's going to be 15 centimeters squared. And then we've got there's one in the middle. I'm going to use red this time. And that's going to be 4 times 3, so that's going to be 12 centimeters squared. Now, don't forget with these questions, this is a very common mistake to make, is that there's also 3 more faces on the other side. If I drew this cube and made it transparent, you would imagine that there's this face as well here, and then if I go up there, there's that face there, and there's the back face as well. Now, in my example, they're all going to be exactly the same, so I could work out these 3 here, and I can just multiply them. Once I've got the total area there, I can multiply the whole thing by 2. So we've got the 15, we've got the 20, and we've got the 5, and altogether that's going to be 40 centimeters squared. And we're going to multiply that by 2, so times 2 is equal to 80 centimeters squared. Okay, so that's going to be the surface area of this cube. Now, what about the surface area of these things here? Well, what you're going to do is you realize each face, in my example, is 1 centimeter squared. And what we're going to do is we're going to add up the front face, and the front face is going to be just the front of each one of these. So the front face of this thing here is going to be 23 centimeters squared. 20 centimeters squared. So let's just go front, and it's 23 centimeters squared. There's also a back, which we can't see, which is going to be exactly the same. So back is also equal to 23 centimeters squared. And then we can do the top. So this is where it gets a little bit trickier. So I'll use my highlighter and we'll see what can we count for the top. Well, we've got this one, 1. We've got this one, 2. We've got this one here, 3, 4, 5. We've got this one, 6. We've got this one, 7, 8, 9. Okay, so we can say that the top is 9 centimeters squared. And then we can do the bottom as well. The bottom is going to be a bit harder to do. Let's do the right-hand side because it's the visible side. Just like with the cube, you can have some invisible sides. So we'll do the right-hand side now. So we've got 1, 2, 3, 4. And there's that one. The right-hand side of this cube is actually blocked. So then we've got this one. I've lost count. 4, 5, 6, 7, 8, 9, then 10, 11, 12, and then we've got this one, 13, 14, and 15. So the right is 15 centimeters squared. Now you can realize that just like with the cubes, they've got six sides. This has got many faces, but it's still going to only have 6 sides. Careful you don't move the frame. So we've done 4 sides. The other 2 sides, we've already done one invisible side, which is the back, the easiest one to do. We've also got another invisible side, which is going to be a bit harder to do. So we've got one at the bottom here. Let's do a tally chart here. We've got one at the bottom, another at the bottom there. We'll have another at the bottom of this one. We'll have 1, 2, 3 at the bottom of this one. So 1, 2, 3. And we'll have 3 at the bottom there. 1, 2, 3. So I'm just going to start writing the other 2. The bottom of this one on the left is going to equal 9 centimeters squared. The same as the top, in fact. Maybe that's probably not much of a coincidence. No. So that's the bottom. And we've done the right. Now we can see this is symmetrical. So the left is going to be exactly the same. Because it's all exactly the same, isn't it? You're going to have 2 there, you're going to have 1 there, 3 there, and 5 there, and then you're going to have 4 here. So Oh wait, not 9. Sorry, yeah, 15 is, yeah, that's right. So then the left is also going to be 15 centimeters squared. Oops. So this is the examples they've given you takes quite a long time actually, but let's just add them all up and we'll work out the total surface area of the one on the left. Okay. So the total surface area is 94 centimeters squared. That's the total surface area. The surface area of the one on the left is 94 centimeters squared. We're going to run out of time here, but if we did the same thing with the one on the right, you'll find that the surface area is lower. And the reason for that is because it's squashed down and more of these cubes' faces have been concealed by other cubes. And whereas this, because he's thin, he's got a higher surface area. So you'll see this in animals. If they're in a hot climate, they will probably have long, spindly arms and legs and be quite skinny. Whereas if they're in a cold climate, they'll be more round and short and stocky. So you think about a polar bear; it's quite a round creature. So is a penguin. Whereas a giraffe or a gazelle, all these or a camel, they have like long, spindly limbs and they're quite thin and stuff. So this is the surface area to volume ratio. Now we can actually calculate the ratio here. We've got if we say the surface area to volume ratio, well, that's going to be 94 to 23. Now 23 doesn't actually go into 94, does it? So that would actually be the ratio simplified. But if you want to talk about how much bigger is the surface area to the volume, well, it's difficult to really say, but we leave it like that, and then when you did the same here, you'll see that it's rather than it being 94, it's going to be a much lower number. So that is kind of a brief introduction to what surface area to volume ratio is all about. Okay.